Physicists have long been fascinated by black holes, a phenomenon that has intrigued scientists for over a century. These massive entities, which defy our understanding of gravity, remain largely invisible to us. A black hole with a mass 2 to 4 million times that of the Sun is incredibly powerful. Yet due to research conducted the past few decades, we've transitioned from knowing virtually nothing about them to uncovering more, sometimes in surprising ways. Just recently, a breakthrough occurred. Researchers, including those at the Kaku Institute, reported that they've managed to peer inside a black hole. This new data has illuminated facets of the universe that science may have overlooked in the past. Let's dive into black holes and discover what lies within. Space is vast and awe-inspiring. Before delving into what was revealed in recent findings, it's crucial to grasp the basics of what black holes are. Many people are familiar with the idea of black holes, yet there are still significant gaps in our understanding of them. The concept of a black hole became theoretically possible in 1916 when Albert Einstein published his general theory of relativity, which predicted the existence of such objects. However, the idea of black holes remained purely speculative until the 1960s, when scientists first observed compelling evidence supporting their existence. While studying the binary star system Cygnus X1, astronomers detected an unusually bright blue star emitting X-rays. This star wasn't a normal celestial body, it was orbiting around a mysterious massive object. After further examination, it became clear that the X-rays were not simply floating around in space, but were being pulled toward the dark entity, confirming the existence of black holes. This was a groundbreaking discovery, showing that black holes were not merely theoretical constructs but real phenomena. The significance of this discovery can't be overstated. It meant that an entirely new class of objects existed in space, requiring urgent and thorough study. Researchers from around the world turned their attention to black holes with renewed focus. The first identified black hole, Cygnus X1, is located about 6,000 light-years away from Earth in the Cygnus constellation. It is many times brighter than our Sun and possesses an immense gravitational pull so powerful that not even light can escape it. This is why it's termed a black hole. The concept of a black hole is both fascinating and intimidating. It refers to a region in space where the gravitational force is so intense that nothing, not even light, can escape its pull. Anything that gets too close to a black hole is inexorably drawn in, doomed to be lost forever. This danger makes the study of black holes not just intriguing but essential. However, are we in any immediate danger from them? Despite the closest black hole being about 500 light-years away, this distance still raises questions about potential risks. The true scope of black holes is still emerging. After the discovery of Cygnus X1, astronomers began searching for other black holes. It's now believed that there may be as many as 100 million black holes in our Milky Way galaxy alone. Detecting them remains a formidable challenge. Estimates suggest that millions of them exist within our galaxy, underscoring the importance of studying these enigmatic objects. The primary concern with black holes is their immense gravitational pull. This pull is so strong that it pulls everything, even light, into itself. The core of the black hole, known as the singularity, is where all the matter that falls into it is compacted into an infinitely dense point. In simpler terms, black holes act as cosmic vacuum cleaners, sucking in everything in their vicinity. If someone were to fall into a black hole, they would be gradually stretched and compressed until they were reduced to a singularity. This process is incredibly slow, meaning the individual would meet their end long before the final irreversible stage. Yet, despite the apparent danger, black holes are so widespread that they cannot be ignored. Even though the closest one is far away, the sheer number of them within our galaxy makes them a significant subject of scientific investigation. In 2019, scientists achieved a historic milestone by capturing the first-ever clear image of a black hole, the supermassive black hole at the center of the M87 galaxy. This photograph was obtained over several nights. With each exposure, new insights were gleaned, and the data was painstakingly pieced together to reveal a clearer picture. The most striking discovery was that a black hole isn't just a single void in space, it consists of three distinct layers. The first layer is called the event horizon, which marks the point beyond which nothing can return. Once an object crosses this boundary, it is inevitably drawn toward the black hole. The second layer is known as the photon sphere, where light is trapped in orbit. Any light that enters this region is caught in the black hole's gravitational grip and cannot escape. Finally, the third layer is the singularity, where matter is crushed down to a single point in spacetime, creating an environment where the laws of physics cease to function. This breakdown of the laws of physics is one of the many reasons studying black holes is so challenging and fascinating. What's even more intriguing is that each black hole behaves differently. While they tend to share the same basic structure, the way each one operates can vary. Unlike other objects in the universe that we can study directly, black holes can only be examined indirectly. Researchers use observations of the radiation emitted by black holes and the gas and dust surrounding them. It's impossible to send a probe into a black hole because anything that crosses the event horizon is pulled into the singularity, where it would be crushed to an infinitesimally small point. This presents a significant limitation for scientists. Without the ability to study black holes in the traditional way, researchers are forced to work with two-dimensional models to understand these three-dimensional objects. Furthermore, black holes come in different shapes and sizes, making them even more challenging to study. Scientists have developed several theories to explain how black holes form, with one of the most prominent being the idea that black holes originate from collapsing stars. When a star runs out of fuel, it can no longer generate the energy needed to counteract the force of gravity, causing it to implode. If the star is massive enough, this collapse continues until the star becomes a singularity. NASA researchers have focused on a particularly powerful galaxy, M87, where they observed a vast whirlpool of hydrogen gas rotating at an astounding speed of 1.2 million miles per hour. Despite the immense forces at play, the gas didn't fly apart. Scientists concluded that there must be a massive object at the center of the galaxy holding it all together. This object turned out to be a black hole weighing billions of times the mass of the Sun. In 1963, New Zealand mathematician Roy Kerr used Einstein's equations to provide a model for rotating black holes. Kerr's theory suggested that instead of collapsing into a singular point, a rotating black hole could form a ring of fire or an accretion disk. This disk would rotate so rapidly that the outward forces would counteract the gravitational collapse. Kerr's work also introduced the concept of the Einstein-Rosen bridge, or wormhole, a hypothetical tunnel that connects two distant points in spacetime, potentially even linking parallel universes. The concept of wormholes has fascinated scientists for decades. If black holes are indeed connected to wormholes, they could offer a shortcut through spacetime, allowing travel between distant regions of the universe or even between different times. However, even if wormholes do exist, it's unlikely that we would be able to travel through them anytime soon. According to Einstein's theory of special relativity, the speed of light is the ultimate limit for how fast anything can travel. This presents a barrier for using wormholes for faster-than-light travel. Nevertheless, wormholes continue to be a captivating subject of theoretical research. If they were stabilized, they could provide a means of traveling across vast distances of space or even to different times. Some physicists also suggest that wormholes could offer a mechanism for time travel. However, the challenges of crossing a wormhole are immense, as they would likely be unstable and surrounded by extreme radiation and gravitational forces. To truly understand the nature of black holes, physicists will need to develop a unified theory that combines both Einstein's theory of general relativity and quantum mechanics. One promising candidate for this theory is superstring theory, which proposes that the fundamental particles of nature are actually tiny vibrating strings. These strings could explain many of the mysterious phenomena observed in the universe, including the formation of black holes and wormholes. Superstring theory also suggests that black holes, wormholes, and other exotic solutions to Einstein's equations may arise due to the bending of spacetime by these tiny strings. Despite its promise, superstring theory requires the existence of additional dimensions of spacetime that are too small for us to detect. However, research into black holes and their mysteries continues to push the boundaries of our understanding. One of the most groundbreaking ideas related to black holes is the concept of Hawking radiation, proposed by physicist Stephen Hawking in 1974. This theory suggests that black holes are not completely black, but emit faint radiation due to quantum effects near their event horizons. This radiation could cause the black hole to slowly lose mass over time, eventually leading to its evaporation. Hawking radiation is difficult to detect, however, due to its weak nature. Still, this idea offers valuable insight into the behavior of black holes and their role in the universe. Black holes also provide a unique laboratory for studying the interaction between gravity and quantum mechanics. The extreme conditions near a black hole singularity are where both gravitational forces and quantum effects come into play, making them a key area of research for physicists looking to develop a theory of quantum gravity. The study of black holes may also hold clues to understanding the origins of the universe. Some theories suggest that the conditions near a black hole could offer insights into the birth of spacetime itself. Additionally, if wormholes do exist, they could provide a mechanism for exploring vast regions of spacetime, offering new possibilities for interstellar travel. Although these ideas are still speculative, they continue to inspire researchers to explore the deepest questions about the nature of our universe.